Welcome to another video on physics. This video is on rotational motion. An angle in radians is defined as the arc length over the radius. So how many radians are in a complete circle? Well, a complete circle has an arc length of 2 pi r. This is the circumference, right? Well, if this is equal to our arc length in a complete circle, then our angle in radians is equal to our arc length or our circumference, or 2 pi r over r. The r and the r cancel out, and theta in radians is equal to 2 pi. So if you make a complete revolution about a circle, the the angle displaced is 2 pi radians. Rad for short. So how many radians are in half a circle? Well, if a full circle equals 2 pi r, then a half a circle will equal pi r. This will be s, our arc length. If we go halfway around the circle, this will be what we traveled. So, plugging this in for s, we get theta in radians, angle in radians, is equal to pi r over r. R's cancel, and you're left with pi radians. So, if you go a full circle, or 360 degrees, you went 2 pi. Go half a circle, 180 degrees, you went pi radians. Now, a little note about the unitless unit. Take a note. Theta in radians is equal to s, which we can call, let's say, something in meters, just some distance, over r, which is also in meters. It's unitless. It is a ratio of arc length and radius. Angular velocity describes how fast an object or body is turning about an axis. If a body turns through an angle theta in a time t, its angular velocity, omega, that's the Greek letter, is this. So the angular velocity is the change in theta over the change in time. This is average angular velocity. So, like we did with the videos on motion, if this is the average, well, the instantaneous is simply d theta dt, and that is also the angular velocity. This is the instantaneous angular velocity. Typical ways you may see angular velocity described include radians per second, revolutions per second, maybe even revolutions per minute, or RPMs. Well, 1 revolution per second. Well, 1 revolution has an arc length of 2 pi r, divided by r would be 2 pi radians. So 1 revolution is 2 pi radians in 1 second. So I could convert that to 2 pi radians per second. For revolutions per minute, I can do the same thing. It's 2 pi radians, and I just divide by 60 to get seconds. Take a minute to think about angular velocity, omega. Now, let's say you have a ball at the end of a string. And you connected the ball to the string, obviously. And it's just hanging there. No theta changing at all, just hanging there. Does it have an omega? Or an angular velocity? No. It does not have an angular velocity because the angle isn't changing. Now, is the motion of the ball changing? No. It does not have a linear velocity. So think about it. If you have an angular velocity, that means your angle is changing in time. So this must relate to our linear velocity. Turns out it's given by omega r. Now this angular velocity has to be uniform. And this is you can only use this when your angular velocity is expressed in radians. See, linear velocity in this context is truly an extension of angular velocity. Think about the implications of angular velocity. So instead of the stone or the ball or whatever being this distance away from the center, imagine you have a shorter string and the ball is this distance away from the center. The angular velocity stays the same, because it doesn't matter where you're at along this string, wherever you place a ball. If you have some sort of angular velocity, some change in radians, that's not going to be affected with the placement of this ball. Linear velocity takes the distance away from the center into consideration. R becomes important. Notice here, it doesn't matter where you're at upon the circle. If this is a CD spinning and you have an object taped down here and an object taped down here, these values will be identical, as both of them are completing the same angular displacement in the same amount of time. The quantity in which is not the same is the distances that they're traveling in that quantity of time. That's why it's important to establish an understanding of how to relate angular velocity to linear velocity. Now this is angular velocity. So what is, if this changes, this angular velocity changes, what occurs? Well, an angular acceleration must have taken place. We use the Greek letter alpha. This is the change in angular velocity over the change in time. This would be average angular acceleration, whereas instantaneous would be change in angular velocity over a change in time. In a previous video, I derived the kinematic equations for constant acceleration through integration. Once again, I'm going to carry out that same series of maneuvers, and this is one of the reasons why calculus is so important for physics. Is the same ideas, the same maneuvers, mathematically speaking, occur over and over and over again. So, like we did for the kinematics, move dt to the other side so you can integrate. So you get alpha dt equals dw, and I'll just call them dt and dw and alpha just to make it easier to say it all. Okay, so we're going to integrate both sides. The left side with respect to time, the right side with respect to w. It's dt dw. We're going to do this one, some point t. We're going to start it at 0. For this one, some omega final value in some omega initial value. Well, alpha here is constant, so it's a number. It's like 5 or 7. We're just going to keep saying alpha, but if it helps you in your head, just call it 7. Well, how do we integrate that? Well, the antiderivative of a constant is just going to be alpha t here, right? So it'll be alpha t evaluated at t and 0, and that'll be equal to, now dw is pretty much nothing, but when we integrate we'll get w. It's just a small differential. We integrate it, we get w. We're going to evaluate that at omega final and omega initial. So simplifying, we get alpha t minus alpha 0 is equal to omega final minus omega initial. This is 0. Solving for omega final gives you omega initial plus the angular acceleration times the time. Now, notice how similar this is to the final velocity is equal to the initial velocity plus acceleration times time. So if any of you are watching and you don't know calculus, or you're not very good with calculus, you can simply just relate them to formulas you may have already memorized. Continuing along, what is omega? Omega is change in theta over change in time. So I will substitute that. I receive change in theta over change in time is equal to the initial angular velocity plus the angular acceleration times the time. I just substituted those values. In the same fashion as prior, as we did just before, I'm going to move the dt to the right hand side so I can integrate. This gives me d theta equals this stuff dt. All you have to do now is integrate some final theta, some initial theta, and on this side you'll integrate to some final time, and we'll just have it as 0. Integrating the left hand side, you get theta. We're going to evaluate that at theta final and theta initial, and that'll be equal to omega initial t plus 1/2 angular acceleration, 1/2 angular acceleration times time squared evaluated at t and 0. It's easy to see that this portion will become 0, t will plug in for t, the right hand side will stay the same. Here we'll have theta final minus theta initial. So this gives us theta final is equal to theta initial. All I did was move the theta initial because it was theta final minus theta initial. Just moved it over to the right. Plus the initial angular velocity times time plus 1/2 angular acceleration times time squared. And if you remember your kinematic equations, this should seem strikingly familiar to this one. So the purpose of this video was A, to introduce you to rotational motion, but B, to show you the importance, and primarily B, to show you the importance of calculus in physics. This is one of the reasons why calculus is so powerful. For instance, as simply as it is, how will it benefit you? Well, if you're taking your test, you forget your formulas, you assume angular acceleration is constant, start integrating back, and then you get your answer. What if they told you angular acceleration wasn't constant? What if it was for some odd reason quadratic? Well, at least this way you could just create a whole new set of equations for a quadratic angular acceleration. No big deal, you just integrate. I hope you learned something from today's video. Keep working on that physics, and I will be back soon with more videos.